Okay, then I think I can start by introducing you, maybe given that it's the first seminar of the series, I will say a few words. I'm very happy to welcome you all to the series of the SITP seminars on Mondays for this new year. I'm co-organizing these seminars together with Henry Maxfield and Chaitanya Murthy, also in the call. And this year we can finally start to plan some seminars to be in person, along with some other seminars to be held online, like today. And today we are really pleased to host Professor Gino Isidori as our speaker. Gino completed his PhD studies in Rome under the supervision of Luciano Maiani, and then was appointed as permanent staff at the INFN lab in Frascati in Italy, where he became head of the theory group and research director. And he held positions of visiting scientist also here at SLAC and in Munich and at CERN. And since 2014, he's a full professor at the University of Zürich in Switzerland. And recently, in 2018, he was awarded a highly selective European grant, the ERC Advanced Grant. And Gino is a leading expert in the field of flavor physics that aims at explaining the structure of the standard model particle content. And I will let Gino introduce these fascinating topics and the recent experimental developments to you. And thanks again, Gino, for agreeing to give us this seminar today.
Thanks a lot, David, for this too kind introduction. Okay, so let me share my slide. Okay, can you see it? Let me see. Full screen now. Yes. Okay, so it is a pleasure to be here, even if virtually, to discuss some, I think, exciting time and exciting result in flavor physics. So this is the plan of my talk. Actually, is a bit long. I hope I'll be able to go through everything. I will first start with a general introduction to the open problem in flavor physics, and then I'll of course focus on these interesting results, which are these LFU anomalies, Lepton Flavour Universality violation anomalies. And then I will, starting from these data, I will start to do some model building in a bottom-up perspective. So, okay, let me start really very basic. I guess you all agree that we have a beautiful theory that is the standard model that describes all what we know. It's a very elegant and simple quantum field theory, which, however, we regard it as an effective field theory. Okay, we regard it only as the limit in the range of coupling and energy that we have explored of some UV completion that contains more degrees of freedom. So this is the modern point of view on the standard model. It is an effective theory because the standard model itself do not address problem like phenomenological problem like dark matter, dark energy, inflation, and it's more theoretical problem like hierarchy and flavor. So what I think that is the structure of fundamental physics, that there is some UV theory that we don't know, and then we have the low energy limit that is the standard model. And what we can say after the first phase of the Large Hadron Collider that is concluded that, okay, the standard model is complete. So we find all the building blocks. The Higgs boson in particular, that was the last missing piece here, has been found, is light. And then there is a mass gap. So certainly there is something there is nothing just around the corner after the standard model. And what we would like to understand is what is beyond this mass gap. And if you want, again, just to remain in very general terms, is what we have identified is the long-range structure of the theory, and we would like to understand if there are some smaller, maybe more fundamental constituent in terms of which we can describe this long-range structure. This is a difficult exercise. I mean, to reconstruct the UV completion having only information on the low-energy dynamics. Actually, it's not even possible to do it without some hint. And we know that very well, because actually this is what, in a sense, we have been doing in the previous 30, 40 years when the standard model was built starting from its low energy limit, that was the Fermi theory. So what we can do to try to understand what's here? Well, in absence of direct signal of the new physics, that is, in absence of the possibility to explore directly high energies, we can still look at low energies and to understand if there are a natural feature in our effective theory that maybe really point to something that we cannot explain with the building blocks that we have. Okay, so if we find something that is still macroscopic or long range, but we cannot explain it, then we understand that we miss some building blocks. Okay, now being more concrete, so let's give a closer look to these effective theory. So the standard model, as you know, it is composed by the gauge and the Higgs sector that, as I said, describe the long-range forces and the light degrees of freedom. And this is really long range here for me means everything at distances bigger than the one of the Fermi scale. Okay, for me that is the reference scale. And of course, technically this means that we correspond to operator of dimension 4 up to 4 in the field theory treatment. And of course, we have to introduce the Higgs sector to describe particle masses, okay, to describe the non-trivial ground state. Now, the full effective theory contains extra pieces that we can write, which are technical, if you want, operator of dimension higher than 4, built in terms of these long-range constituent, the quarks, the leptons, and these gauge bosons, which you can see has the remnant of the heavy dynamics at low energies. And we can really think of this as contact interaction, okay? Contact interaction corresponding to some heavy dynamics that we are not able to resolve because we don't have enough energies, and therefore that we describe as contact interaction. And these are weak effect, I mean, very weak effect at low energies. So when I say that we want to look at the unnatural feature of the effective theory, so this unnatural feature can be viewed as imprint of the UV theory, okay? We would like to read this effective theory, understand what comes from the UV. And I think from a quantum field theory point of view, there are two distinct features. On one hand, we can look at the coupling here and to see if there are some unnatural aspect in these low energy couplings that we can interpret as the imprint of the UV theory. This I call it a qualitative imprint because clearly it's difficult to extract what comes from UV from just I mean, a generic description of what we see at energy because of the normalization, because of course the value of the coupling here is determined by UV, but is in a non-trivial way. Still, some information I think it's there. And then there is a more direct imprint of the UV, which are the coupling of this higher dimensional operator, because these terms will not be there if there was not, they would not be there if there were no extra degrees of freedom. So the evidence of a higher dimensional operator, which actually we can detect precisely looking at violation of the accidental symmetries, is a more quantitative imprint of the UV completion. So these are, if you want, our instrument, try to understand, get information on the UV looking at low energies, determine the coupling of all these terms here. I mean, concerning the unnatural aspect of low energy coupling, probably the most famous example is the instability of the Higgs mass under quantum correction. So we know that the Higgs mass, the physical Higgs mass that we measure come from a parameter in the Lagrangian, the Higgs quadratic term, plus correction, which are quadratically sensitive to the new degrees of freedom. So the fact that we have a quadratic sensitivity to possible high energy degrees of freedom is what has been interpreted for a long time as the signal that maybe this new degrees of freedom cannot be too heavy. Okay, otherwise we need this fine tuning between these two sectors here. And of course, this is why I call it a qualitative imprint, because still we can accept the fine tuning if you want, and therefore it's hard to say precisely where the new degrees of freedom are. But certainly it's an indication of something, some new physics that, if you want to stabilize this, should couple to the Higgs and the top, at most in the TV domain, so not too far from the electron scale. But that was just an illustration of what again, probably everybody knows, that we have this indication of this hierarchy problem that actually we start to doubt. But what I want to emphasize in this seminar, that actually Flavour physics, the Flavour observable, particularly the information here on the Flavour coupling of the Higgs and the possible evidence of high dimensional operator, is telling us much more than just the Higgs mass. And not only that, but I think it will tell us even more in the future, because now we really have a series of high precision experiments that can explore with high precision this term here, especially in this Flavour sector. So let's give a closer look to Flavour. It's not Flavour I mean, by Flavour we mean the problem that we have different generation with strange coupling and strange masses. This is a well-known problem that's been with us since really a long time. So again, still remaining in general terms, how we define flavor. Well, technically, we can define it as the U3 to the 5 symmetry that we have in the gauge sector of the standard model. So the gauge sector described is completely dictated by the number of light degrees of freedom, which are these quark and lepton families, and their charges under long-range interaction. So once I tell you we have 2 types of quarks and 2 types of leptons with certain charges, I know exactly how they interact with the gauge boson, okay? And we have 3 copies of that, okay? And they are described by 5 field, okay? And this is why we have this U3 to the 5 symmetry. So this structure, this symmetry is really an accidental symmetry in the big global symmetry of the gauge Lagrangian. Then what distinguishes the different families, is the Higgs, because the Higgs is this scalar that interact with the quark and the gauge boson and describe particle masses. Now, as far as the flavor, the interaction between the Higgs and the fermions is described by the Yukawa interaction, which are 3x3 matrices in flavor space, which determine the masses of the fermions we observe. And the masses, are very hierarchical. So from the top to the electron, there are 5 orders of magnitude. So the Yukawa coupling really seems to have some imprint from the UV, which is non-trivial, okay? Because they are not random numbers. They really exhibit a hierarchical structure with the top Yukawa coupling order 1, and then, for instance, here I'm just looking at the up quark Yukawa coupling. Here the up quark mass, which is 10 to minus 4 times smaller than the top. So clearly, it's a hierarchical structure, which doesn't appear to be accidental. This is sometimes called the flavor problem because we don't have an explanation in the standard model itself why this is so, and clearly this seems to point to something else. So, just looking at the standard model Lagrangian, we have these 2 facts. We have a large accidental flavor symmetry in the gauge sector, and the flavor degeneracy broken in a very peculiar way by the Yukawa interaction. And this interplay between the global symmetry and the peculiar breaking that give rise to a series of exact or approximate properties that we call accidental symmetries, exact or approximate, which seems to be quite respected in nature and are very peculiar. Like, for instance, the conservation of lepton flavor, again, is an exact symmetry that we don't impose in the Lagrangian. It comes for free just because there is no way to break via dimension 4 operator this flavor symmetry. Okay, the Yukawa coupling cannot describe a violation of lepton flavor. This is an exact symmetry, well known, but there are also a series of approximate symmetry. For instance, isospin. The symmetry between up and down arise accidentally simply because the up and the down Yukawa coupling are both very small. And I think there is not really conceptual difference between exact and approximate symmetry. They both arise because of this peculiar breaking, which hint only to certain specific direction and cannot highlight different direction, cannot identify different direction. So the exploration of this accidental symmetry is very interesting. Why? Because, again, we call accidental symmetry which are not fundamental properties of the theory, but emerge accidentally through energy, simply because we don't have enough variable to describe the violation of the symmetry. So is this part of the Lagrangian, the long-range structure, that define this accidental symmetry? Now, if in the theory there is something else at higher scale that violates the symmetry, we expect it to manifest itself via violation of the symmetry via this contact interaction. So the new degrees of freedom here will induce a violation of the symmetry, which cannot enter here in the dimension 4 part of the Lagrangian simply because we don't have the variable to describe it, but will enter at some point in this multiple expansion, if you want. It's a bit like a multiple expansion, okay? And so searching for violation of a symmetry is really a very powerful way to reconstruct this possible ultraviolet degrees of freedom, because clearly from the experimental point of view, if you have a violation of a symmetry, you can detect it even if it is a very tiny effect, and you can distinguish from the leading contribution coming from the dominant part of your interaction. And this is well known. There are a lot of examples in the past. Just to highlight the most famous one, I mean, if you take as the Lagrangian theory QED and QCD, Okay, who actually was indeed a long time ago. That was easily when it was not called QCD, but it was strong interaction. Flavor is an accidental symmetry. Actually, the individual quark flavor is an accidental symmetry of this theory. And indeed, this is why weak interaction emerge in the charged current, because they violate flavor. And actually took a much longer time to identify the neutral current, because they do not violate flavor. So they are hidden by this other type of interaction. Okay, so clearly searching for a violation of accidental symmetry is very powerful. And I'm stressing all this because this violation of Lepton Flavour universality, which are recently reported in B-physics, these B-physics anomalies are exactly of this type. So it's a violation of an accidental approximate symmetry of the standard model Lagrange. Now you can say, well, okay, fantastic. So we should expect a lot of these things. I mean, if there are many degrees of freedom here. So in principle, indeed, we could expect many violations of accidental symmetry, but we have not seen many except for this violation. So in principle, there could be new flavor violating effect, and we don't see. And actually, for a long time, indeed, we just put bounds on this effective operator, looking at precision observable in flavor physics. But the most remarkable example are these bound on 4 fermion interaction that contribute to meson-antimeson mixing. So if you put a generic 4 fermion interaction, you destroy the agreement with data on meson-antimeson mixing unless you put here a very, very suppressed coupling, and which is illustrated here by this plot. So the bounds that we get on this higher dimensional operator seems to point to very high scale. Okay. And this fact is sometimes called as new physics flavor problem, because actually we would like, on the other hand, to have some degrees of freedom relatively close by to stabilize the heat sector. So how come that we don't see it? And well, one point still on accidental symmetry is the fact that accidental symmetry allows to separate different sectors of the DFT. This is a very important point that I think is often not emphasized. We can have stable scale separation. The most famous example, which I think everybody knows, are lepton number and neutrino masses. As you know, lepton neutrino masses are not described here by the normalizable part of the standard model Lagrange. To describe neutrino masses, we have to introduce one of these higher dimensional operators, in particular dimension 5 operator, and therefore to describe neutrino masses, and actually to reproduce the correct value of neutrino masses, we have to put the, if you want, if the coupling it's 1 here, this is the Higgs wave, we have to put a very, very heavy scale here. And there is, however, we can do it without problem, without introducing, for instance, a problem on the other observable, because we can think that there is some new physics at lower scale which conserve lepton number, and these operator here come from a much higher scale where lepton number is violated, and this separation of scale is stable. Okay, because indeed, because this is an accidental symmetry, therefore the introduction of new degrees of freedom at a lower scale which do not violate the symmetry do not destabilize this picture. So I'm stressing this because actually we are very familiar with this concept in the case of exact symmetries, for instance, lepton number or Bayer number. But the same can be true also for approximate symmetry, like the approximate flavor symmetry that we observe, the suppression of flavor changing effect. So the same scale separation up to a certain degree, because the symmetry is not exact, can be preserved for the flavor violating term. So concluding this general introduction, if you look at this standard model effective theory, we have the gauge sector where we see big symmetry, which may be accidental. We have a peculiar breaking of this symmetry by the Yukawa coupling. And then we have a series of stringent bounds and maybe a few anomalies in these higher dimensional operators. So the big question we would like to understand is, are these symmetries all completely broken in the UV? And if they are broken, at which scale are they broken? Can we make sense of the fact that in certain sector we don't see anything, and in other sector we maybe see a violation? These are really the interesting question on which finally the recent data start to provide some answer. So this is, I would say, I hope I give you a very brief introduction on the game we are trying to play with. I think the recent data start to highlight some evidence here in this series, which I think fit well with the structure of different scale in the underlying theory. So let's look at the data. Okay, the data are these LFU anomalies. So since 2013, in a series of semi-leptonic BDKs, it emerged some violation of Lepton Flavour universality. So that is, we observe a violation of the universal behavior that we would expect in the standard model between different lepton species in processes like B2S, lepton antilepton, or B2-char, lepton neutrino. So here, in this B2S LL process, the difference is between mu and electron, the anomaly, and in the B2-char, the difference is tau versus light leptons. So what is technically Lepton Flavour universality? Lepton Flavour universality is an approximate accidental symmetry of the standard model Lagrangian. It's the symmetry that we have if we switch off the Yukawa coupling of the leptons. This symmetry is badly broken in the Yukawa sector. If you look at the Yukawa coupling, they differ by several orders of magnitude. However, they are all very small compared to the gauge coupling. So actually the biggest one, the tau Yukawa coupling is 10 to minus 2, the gauge coupling are over there 1. Even in the QED coupling. So these are clearly very tiny effects. So there is a very strong violation of Lepton universality, which however, overall is very small. It's a bit like isospin, okay? So maybe there is nothing fundamental in Lepton Flavour universality, simply that the Yukawa coupling are accidentally small. So it's not surprising that maybe we see a violation when we look at higher dimension operator. So, but keep it to the standard model, because of this smallness of Yukawa coupling, one expects that on the dynamical point of view, we can neglect the Yukawa coupling. The only relevant effect is our kinematical effect, and therefore we should expect the same behavior for, let's say, mu and electron in this process, or tau versus light leptons. On the other hand, data start to exhibit some deviation. So the simplest, cleanest observable are this ratio of a hadron with a B quark, they came to a hadron with a S quark and 2 muons, normalized to the same process where we exchange muons with electrons. You see, the situation in 2017 was this one. So we had this ratio for which we expect 1 in the standard model. Well, in this case, slightly less than 1 because of a kinematical effect. And we see some 2 sigma deviation in 3 different observables. Now the situation has changed, has improved in the last 3 years. One of the deviations has become 3 sigma, other deviation accumulated, and altogether, clearly we have a significance, a large significance of deviation from the standard model. I will quantify exactly in terms of sigma what this is later on, but you see immediately that we have quite a lot. I mean, all this is measured by one experiment, which is LSEB. But another observable where LSEB plays only a partial role is the branch ratio of BS to mu, okay, where again we see a suppression of muons. You see, this is the combination of Atlas MS and LSEB, and this is the standard model prediction. So there is a clear deficit. This can be described essentially by the same type of dynamics. Here we don't normalize to electron, we normalize to the standard model prediction, which is quite precise. And finally, there are other observables where it's more difficult to get precise prediction, but still, to the best of our knowledge, we also see here something which seems to be explained by the same underlying dynamics. Here is more difficult because there is contribution from long distance, but again, to the best of our knowledge, this is really described by the same type of dynamics that is described by this process here. And this is a completely different type of experimental systematics. Okay, these are involve only muons, so the angular distribution or the absolute branch ratio of the muon. So they are really solid from the experimental point of view. And what is really striking is the consistency of all this result. I think I've seen a lot of anomalies in the past, but never something of this type where we really have different observable. Still, is mainly the same experiment, but in a completely different configuration. Okay, what enters here, this is dominated by the electron resolution, here is dominated by the muon, so it's really different. So then we can try to put the things together. Actually, these processes are complicated processes in the standard model, are non-perturbative, but we can compute certain things in perturbation theory, particularly the leading contribution of this operator that we generate when we integrate out the W and the Z. We can extract this coefficient quite well from the data. And again, you see here, if we attach to the Z of the photon, electron, or muon, we expect exactly the same result. So there is a in these plots here, you see a conservative fit using only the clean observable, there where we don't really need to care about contribution from charm and intermediate state, which are difficult to control. And right now, if I test the standard model against the most motivated new physics configuration of this coefficient, which is the pure left-handed structure, so a shift in the vector and axial contribution of opposite sign, we get 5 sigma. Okay, combining all the results, so it's not the one result, not one experiment that gives 5 sigma, but altogether it gives 5 sigma. If we put also the other observable, those which are less pristine from the theoretical point of view, but still, I mean, are to the best of our knowledge, are well described, the significance goes even more than 5 sigma. In this case, to describe data, we need not only a left-handed shift, which is this one. So maybe I forgot to say that this is clean because it's a shift between muon and electron. So we really look at the difference between muon and electron. This is what we can compute and control very well. So if we put all data, we see not only this, but we also see a universal correction to C9. So a correction which is the same for electron and muon. Although in this case, the significance is much weaker. So this band here are the clean observable. These other band are the other observable. Actually, see they superimpose very well, and they are very far from the standard model. Now, if I am super conservative and I take only the clean observable and I allow all possible type of new physics of short distance origin, so that is, I try all possible effective operators, the significance goes a little bit down because there is a sort of local square effect, but still is 4.3 sigma, which I think is a very conservative estimate, and it's quite solid. Finally, very briefly, so this I told you about B2SLL. There is the other class of anomalies, flavor anomalies, which is B2 char lepton neutrino. In this case, the anomalies is attributed to tau. So we look at ratio between B2 certain hadron with the char and tau versus B2 the same hadron with the light lepton. And this is the combination of the experimental result. The red is the average. This is the standard model prediction. This is a 3 sigma excess. The progress here is much lower, unfortunately. Hopefully, maybe in next spring or summer, we will have some new result. It's interesting that, first of all, the effect is much larger in absolute term, because here we compete with something that is 311 in the standard model. And also in this case, the data seems to be well described by a pure left-handed amplitude, okay, like in the other case, at least dominantly. But other options are possible, so there can be other subleading effect. Okay, so this was a brief overview of the data. Let's now try to describe this data in terms of effective operators. Okay. So anomalies are seen only in semi-leptonic operator, this quark-lepton operator. We definitely need the left-handed current, although maybe there is some effect also with the left-handed current, but for the moment, for sure, you cannot do without left-handed current. Now, left-handed current is nice because once we have a left-handed current, you always have a neutral and a charged companion because of SU2 invariance. The flavor structure is interesting because we have a large effect in B2 charm and a much smaller effect in B2S muons. You see the B2 charm anomaly is B2 charm tau, so a lot of field of the third generation. So it's B charm is second generation, but tau and new tau is third generation. While in the case of B2S mu, we have B2S mu mu with the 2 leptons out of the second generation. So this is nice because it points to the possibility of something which is large for third generation and smaller when we add more second generation field. And therefore, of the possibility of a link to the pattern of the Yukawa coupling, which I told you is one of these open issue in the standard model. I mean, something that we cannot explain. And maybe the same dynamics explain the Yukawa coupling can also explain these anomalies. Let's be bit more quantitative on the type of operator on the type of effect that we see. So the effect in BS mu, the cleanest one, is a super weak interaction, really in the classical sense of the super weak theory a la Wolfing. So it's a pure local interaction, 10 to the minus 5 times, or 10 to the minus 4 and 10 to the minus 5 times the Fermi coupling, which point to this violation, this non-universality between mu1 and the electron. And so this is what is this band here. Now, if I interpret the coupling in terms of a coefficient of this operator, so I write the operator in this peculiar form that we will see it's motivated when we look at also the other data. So it's an operator that contains two quark and two leptons. So I call the coupling 2, 3 mu mu because here I'm also adopting the basis of the down quark. So 2, 3 means BS and mu mu means mu mu. So this is the coupling I determine in units of then you see it's basically everything is unit of the Fermi coupling. So here is I see 10 to minus 2 times 10 to minus 3, so it's 10 to minus 5 as you see here. Then this is the cleanest information on the anomalies. Then we have this other less pristine but intriguing effect when we put all the data together on B2S LL transition, that we see this universal shift on C9. So the same shift for electron muons. Now this again, it's not particularly significant it's roughly a 2 sigma effect if taken alone, while this other one is the 5 sigma effect. This one can be described, it's nice because it can be described by the same operator here, but with taus. Okay, if I put 2 taus and then I close the tau loop, I will generate a correction to electron mu, which is universal. And I need here a much bigger coupling because I pay a loop suppression. So if I put the same operator here but with 2 taus, and so the 2, 3 tau tau, I induce a universal shift to C9. Of course, I can do it another way. But why I like this way? Because this way, this 2, 3 tau tau was already predicted exactly of this type, looking at the charged current anomaly. Because here clearly, if we look at the charged current, this can be char tau neutrino. The size and the need of this operator was already predicted from charged current before this effect was observed in neutral current. So let's now look at the charged current. In the charged current, again, we used exactly the same operator with, again, slightly different Flavour structure, because indeed we can have this 2, 3 tau tau, but we can also have the 3, 3 tau tau and then use the CKM rotation, because I told you I adopt as a conventional basis the one of down quarks, therefore I need to rotate to the up quark. So if I have 2, 3, I have to put VCS. If I have 3, 3, I have to put VCB. So you have a weighted combination of these two coupling here. So I have a band here that describe well my data. I cannot have a too big 3, 3 tau tau because otherwise I hit bounds from direct searches at IPT, because actually this is, you see, this is suppressed by VCB. So if I want to describe the anomalies, this has to be large. It cannot be too large. So we really need both of them to describe well the data. And then the relative weight of the two is some 10 to minus 1. And then finally, you can put the information on this 2, 3 tau tau that was coming from the neutral current. And then if I put the two things together, there is a nice consistency. So it's a beautiful consistency of 3 different effects. So there is the pristine effect on BS mu mu, the less clean but interesting effect on the global analysis of B2SLL data, and finally the charged current. All of them seems to be described by this type of operator with different Flavour structure, where I put a 10 to minus 1 suppression for each second generation field, either quark or lepton. So I start with the biggest effect here, which is the 3, 3 tau tau, that is 10 to minus 2 in units of the Fermi scale. Then I pay a 10 to minus 1 suppression when I go to 2, 3, and then I put 10 to minus 3 suppression when I go to 3 mu mu. So this is basically the summary of the evidence of anomalies, which really are well described by this operator. Here, to highlight once more, which is the rationale here. The rationale is that we think that there is, okay, we clearly observe this effect, BS mu mu, and there should be a coupling and a scale. If we assume that there is the same effect with third generation and the effect is bigger, okay, the indication is that this separation between the two is 10 to minus 3, and therefore actually the scale, the overall scale, it's quite low. Of course, this is an hypothesis, but I think it's really a natural connection, because actually scale more or less like the CKM matrix, that we pay 10 to minus 1 each time we mix a third and second generation field. And of course, there should be also intermediate things, the B2S tau tau, the B2S tau mu, okay, which has not been seen yet. And it's nice that when we put these two things together, we really have a nice description of what happens in charged current. And this one, when we close the tau loop, is the one that gives the B2S universal contribution. So we have these 3 effects, which stress once more, are independently determined, also experimentally, which seems to fit together with this nice story. The B2 tau is the biggest one, the biggest operator that would have to put into the game, which give a prediction of something visible in high PT experiment, because this can induce a tau modification of the proton product to tau production cross section via B quark inside the protons. And finally, this effective scale around TV maybe point to a possibility to stabilize the Higgs sector, which is still a hope because we don't have yet a fully working model, but I think it's an interesting effect. Okay, this is the nice things. Of course, I should tell you also what we do not see. So in the pattern emerging of data is this type of operator with a 10 to minus 1 suppression each time I put a second generation field, at least between the third and second generation. There is a nice consistency between the two set anomalies. What we do not see, and seems to call for an additional suppression, are 4 quark operator. So if I put 4 quark and I put the same normalization, I'm dead. Okay. If I put for lepton, the same. Note also here, I put a specific contraction of operators, which is a leptoquark current. So if I can decompose this also as a QQLL operator. If I do that, then again, which means I spoil this combination of singlet and triplet operator from the point of view of residual, I'm also in trouble because I hit the bound from the S neutrino to neutrino. So this is telling us that we really have to build a model, if you really want to explain all this data, that produce this at 3 level and all the other beyond 3 level. And this is what naturally point to this idea of leptoquark, because this you can clearly describe it well with the 3 level exchange of leptoquark, which on the other hand would generate this effect at the 1 loop level. And therefore then everything starts to be consistent. Okay, so this finish my EFT consideration. Now I enter into more BSM type contraction. So I told you my approach would be really a bottom-up introduction to the problem. And I think it's really nice because this shaken a bit our understanding. If we take this seriously, change a bit our ideas on BSM. So if we want to move from the EFT toward a more complete model, we have to address 2 issues. The flavor structure, I mean, to justify what do I have this 10 to minus 1 scaling, and the nature of the mediator. And they basically hint, both of them, the mediator will be the leptoquark, and the flavor structure has to be something connected to the Yukawa couple. Let's focus on the flavor structure first. To focus why, I mean, to emphasize why this is really is a kind of change with respect to many BSM construction. Let me remind you what was the paradigm for Flavour Physics BSM for several years. The paradigm was this MFV, minimal flavor violation idea. That is, let's assume that we know that there is a standard model, effective theory. We assume that there is some new physics that stabilize the Higgs sector, but these new physics do not break flavor. The breaking of flavor happens at a much higher scale. If you want, this was a kind of economical way to deal with the problem, simply dividing the problem, postpone the flavor generation at some high scale. This conceptually works, okay, because the Yukawa coupling are dimension 4 operators, so you can put them up to a high scale. And so this gives rise of this idea of a flavor blind new physics, which basically share this U3 to the 5 symmetry up to very high scale, except for breaking by the Yukawa coupling. So the idea is to concentrate on the Higgs, forget about flavor. So again, buying this idea that the fermions are identical copies, the 3 generation. I think this is really, I mean, was working, but maybe it's an accident, okay, this fact that we see identical copies. And to emphasize this point, I like to show you this, to present it that way. So to appreciate a bit more the change of perspective. So let's consider the following idle experiment. So suppose we can test matter using only long-range photons, okay? And then we look at positron and proton. So what we can say, if we just have a long-range photon that cannot excite the proton structure. So what we can say that we conclude that we have 2 identical particles from the point of view interaction with the photon, because they have the same charge, that these differ only by their mass. So you can start of thinking of a symmetry here, okay, of a flavor symmetry. which of course is not the case. They are completely different when we go to higher energies. But you see, this is the same argument that we use in the standard model. Now, if I take as long range the full standard model gauge sector, and I consider my 3 different leptons, and of course all the quark and so on, the 3 families, the fact that we see them as identical copies could really just be an accident, okay? Simply because we are only probing the long range interaction with the long range boson surviving at low energies. So this idea that we have 3 identical copies, but for their mass, could be completely wrong. They could be really, they can be described by different field in different combination, which accidentally combine to have these accidentally. By construction, what we see are only the massless state, which have the same charge. So that I think is the possible change of description. And if we want to abandon this, we change picture. So the picture is a multi-scale idea where indeed there is some new dynamics at different scale, which interact differently with the different generation. So the idea is that there is some dynamics close by interacting with the third generation, and then some dynamics at higher scale interacting with the second generation, and then dynamics at even higher scale interacting with the first generation. So the fact that we don't see anomalies when we have light fields, simply because these light fields interact with new physics at higher scale. And this fits very well with the possibility to stabilize the Higgs sector, because the Higgs talk strongly only to the top. So actually it's only the third generation that need to be coupled to relatively light new physics, okay? And in this way, we also can explain why the Yukawa coupling of the light families are heavy, really because there is an intrinsic difference in scale, and this picture is stable. I mean, remember what I was saying at the beginning about the stability of a multi-scale construction, because it's protected by the accidental Flavor symmetry, okay? And this is a kind of old idea which has been discussed in different contexts, and that really fits well with what we observe in terms of anomalies. So basically what we seem to observe is just this first layer, which now if I zoom in, there is some new physics around the TV scale, coupled mainly to the third generation, and interact with the first families only via residual breaking of flavor, which are the residual subleading effect in the Yukawa coupling, okay? And so actually the symmetry that we observe here is not anymore U3, but is U2. And so we can treat this actually systematically. This was something that was proposed before the anomalies was observed, that we proposed with Riccardo Barbieri already quite some time ago. And indeed, it's just taking advantage of what we see in the data in the Yukawa coupling, where we have a big entry and then smaller terms, which can be seen as terms that break an approximate U2 symmetry. So instead of having minimal evaluation, we have a kind of U2 MFV at this scale here. Okay. And of course, the more you go up, at some point there will be no symmetry at all. So this could be the dynamics that describe the anomalies. Now we have to enter into the detail of the dynamics. So this was the motivation of the Flavor symmetry. The detail of dynamics already highlighted. I mean, the leptoquark is the most motivated candidate. We don't have many possibilities because we have to do the effect at the 3 level, because the contribution in the charge current is big. Of course, we can do the simultanic operator with a W prime or Z prime or a Higgs, but then this would be a problem because it would contribute at the 3 level also to B-sub-S mixing, while the leptoquark do not contribute at 3 level to B-sub-S mixing, so it's a much safer player to explain what we see. And really, there is one type of leptoquark, actually maybe I discuss it later. Let me just point out that there's been indeed a kind of renaissance of leptoquark in a lot of different ways to describe this anomaly, because we see the leading effect in simultanic operator and we don't see anything elsewhere. But now if you really want to describe, I will not enter into any of this detail except one model which I like particularly, which is the model of this U1 2/3 leptoquark, which is the leptoquark that can explain both anomalies at the same time. Is the only one. The other require really pairs of leptoquark with the big awkward combination. On the other hand, this mediator we already pointed out in 2015 really can fit well with this U2 flavor structure, at least in a bottom-up perspective, and not only I mean, it's not an accidental mediator, it's the one appearing in the SU4 group unifying quark and leptons. So indeed, if I for the moment, still in a bottom-up perspective, I only take this mediator and I put a flavor structure compatible with this approximate U2 breaking, putting breaking in terms of the order of what we see in the Yukawa coupling. Then I can try to describe the data. This is what we see. So this is just an effective Lagrangian of the leptoquark coupled to quark and lepton with this hierarchical coupling. There are essentially 4 relevant parameters to describe the observable. Here you see how we fit well the anomaly, that is RK and RD, compared to the standard model. We can also have some right-handed current, and so we introduce an extra parameter. We don't improve the fit, but actually we make it even a bit more worse, but still it is a possibility. The most important thing is that we can, from low energy, we predict completely the ratio of coupling divided by mass of the leptoquark, and then we predict what has to be seen in high energy. So this band here is the prediction for high energy observable. We don't put high energy observable in the fit, and this is the prediction. This is the signal of tau-tau pairs in proton-proton collision. You have to excite big quarks from the proton, from gluon, PDF, and then especially the T-channel exchange is the dominant contribution. And you see the coupling to the third generation is big, it's between 2 and 3. The mass can be between 2 and 5 TeV. That is the region. This is the exclusion bound at present, and this is what one should expect to cover at the end of the high luminosity phase. It's not easy to make progress here. It's even more complicated to make progress with a pair production, because at some point one has a kinematical effect. But with a T-channel exchange, this range will be covered. If there are right-handed current, actually a significant fraction is already covered. But here the leading, I mean, the most dominant part of the region is not covered yet. And of course, one should expect that other interesting low energy observable, like lepton flavor violation, like BS to tau mu or tau to mu phi. And of course, everything depends on the value of the anomaly. If it is 10%, or if it is more than 10%, the effects are bigger. If it is less than 10%, the effect will be smaller. But I think it's an interesting setup that predict things around the corner, and which is not yet excluded by present data. Last but not least, let me, in the last 10 minutes or so, let me make really some discussion about the true UV completion, because for the moment I just put in this field and coupled to quark and lepton with some motivated hierarchical flavor structure, but that's not enough. I mean, so certainly this is a massive vector leptoquark require a UV completion. And as I told you, these massive leptoquark fit well in the gauge group proposed by Patti Salam in the 70s to unify quark and lepton. So the idea of Patti Salam was the lepton number as the 4 colors. We organize quark and lepton in SU4 multiplets, fundamental representation. And so when this SU4 group contains QCD, B minus L, and the broken generator surviving are exactly the 6 degrees of freedom of this unique leptoquark field. It's exactly this one. So it's perfect. The only thing that, however, doesn't work is that this model, there is no flavor. So the original Patti Salam model, you would couple this leptoquark universally to all the generation. So you would be completely killed by for instance, K long to mu E. K long to mu E, it's the coupling of the second generation leptoquark to second generation leptons, or first generation quark and first generation lepton. This, to be consistent with data, requires a mass more than 200 TeV. So certainly it's ruled out. But because indeed we don't want to do a universal model, so we really have to distinguish how the leptoquark couple to the different generation. How we do that? Well, the simplest way to do it is to enlarge the gauge group from SU4 to SU4 times SU3 in kind of close analogies of what happens in the case of QED and the weak theory. That is, we have an SU4 and SU3. The SU4 and this separation is flavor dependent. That is, we charge under SU4 only the third generation, and under SU3, the other generation. Color is the diagonal subgroup of this group here. And it's really very similar to what happens with QED, which is the diagonal subgroup of SU2 left and, if you want, SU2 right. Here I can think of SU4, SU4, or SU4, SU3. Here SU2, SU2, or SU2, U1. You see, here the separation is in helicity, if you want. Here the separation is in flavor. Okay? Clearly, the only two true long-range interaction are electromagnetism and strong interaction. And so here we unify weak and the electromagnetic interaction. Here we unify the strong and, if you want, this new super weak interaction. And from this breaking here, the generator of SU4 that we break correspond to lepton quark field coupled mainly to the third generation, with small mixing really to the light generation. The price to pay, however, is that we break more generators, so we have also extra heavy gauge boson. And before discussing the phenomenology, first, there are a lot of, this is really is the main idea, okay? Really the main idea that we somehow deconstruct the color, okay, into this structure here, similar to what happens, in a sense, in analogy to what happens in the case of QED and electroweak interaction. Of course, beyond that, there has been a lot of other options which have been discussed in the literature. I will not want to enter. Let me only emphasize one on which we are working now, which I think is a very interesting possibility that of a UV completion in terms of model with extra dimension, where instead of 3 energy scale, we basically have 3 branes in a compact extra dimension. So the idea is that we have this setup where we have the first family localized more in the UV, the second family in between, and the third family is, on the other hand, is on the TV brane. And clearly, we have a breaking of Pati-Salam mainly here. So the lepton quark is decoupled by the first family, and the breaking of the electroweak symmetry mainly here. So the third family sees a bit the lepton quark and sees a lot the breaking of the electroweak symmetry, and therefore has a big mass. And actually, okay, I don't have time to enter into the detail, but I think it's really, and of course, this is a speculation. I mean, doesn't need to be a 5-dimensional model, but I think it's a nice way to see this. From the point of view of phenomenology, and I'm really done. I mean, the most important point, as I said, is that now when we break SU4 to SU3 and SU3 to the standard model, we generate not only the lepton quark, but also a Z prime and the coloron. So we generate a heavy octet from the breaking of the SU3. And this heavy octet, again, is coupled mainly to third generation, but with the non-vanishing coupling also to the first 2 generation. It coupled in a universal way, which is good, so it doesn't mediate flavor violating effect, but it couples and then can give rise to high PT signature. In this model, really, it's a complete normalizable 4-dimensional model that describes all the data. There are a lot of ingredients, so there are various fields, but a lot of things are fixed by the structure of the Yukawa coupling. So at the end, there is not much freedom to play with. And once we produce all the features of the effective theory, one can calculate delta F2 process and make further prediction for IPT data. Just to highlight one of these predictions, as you see here, is the PP to top, because the coloron can indeed convert the light quark to heavy quark. And actually here, probably this is one of the strongest bound on the model, which push the mass of this guy in the 3TV domain, which starts to be, it's not in tension with the anomalies, but start to constrain even more the setup. Okay, so with this, I conclude. I hope I am in time. I rush a bit toward the end, realize, but so I hope I give you the message that flavor is an essential ingredient to understand the structure of the SMEF, and too often ignore. I mean, and I think it's really important. And the fact that it's important, we already see it from the Yukawa coupling. Okay, so we should not ignore that. And these anomalies really further reinforce this statement. The statistical significance of the anomalies is really growing in the B2SL system. I think the chance that this is a pure statistical fluctuation is really marginal. If combined, the two set of anomalies point to non-trivial flavor dynamics around the TV scale, involving mainly the third family, which really open the possibility to connect to the origin of flavor. which I think it's a very nice picture. And this multi-scale picture, I think it's something that is a bit different from the previous type of model building, which I think it's quite worth to be explored. As I said, there is no contradiction with existing data, but new phenomena should appear relatively soon. So I think also the good thing is that we will know if this is true or not in a relatively short time. Okay, so thank you very much for your attention.
Thanks a lot, Gino. Let's have a round of applause of the virtual.
Thanks.
Thank you very much for the very nice talk. And yeah, I will leave the if there are any questions, you're welcome to ask them.
Yeah, thank you, by the way, for a very nice talk and an optimistic talk. Yeah, I just wanted to ask, could you give us some sort of scenario without waiting until the end of the high luminosity LHC? What could be a sequence of events that would cause a phase transition to the community that this is for real?
It's a good question. Yeah, and sometimes I think about it. I don't know yet what has not been yet, but no, jokes apart. I think well, the things on which we will have a result sooner probably are more flavor observable, still mainly by LSCB. Okay, just for a question of time, because they really are on top of certain analysis. I think on the B2SL system, they have really the chance to close the game alone, because I think they are other observable that can different LFU ratio on different channels. I think for me this would be really convincing, and I think this we can have it really, I would say, in 1 year or two. Of course, ideally one would like to see it also from Bell too, but this would require more time, because the statistics Bell 2 it's going well now, Bell 2, but before accumulating enough statistics, this is not probably before 3-4 years at least. The other things which I mean, the other type of anomaly, the charged current anomaly, again, this is very difficult also for LSCB. This is when the progress has been extremely slow. I mean, the latest data is 2015, and it's after 5 years, we still are waiting the update. On the other hand, there is the hope that also CMS especially can do something. They have these parquet data. I know that they are working a lot now. So I think some movement in the IPT community, I start to see it, which means so more people are there. It's really a manpower problem, amazingly enough. I mean, it's if they would put probably more people to, it's a complicated problem, but I mean, also a lot of manpower problem. So I think maybe in 2-3 years also we will, once this will appear, I think then will be, I hope the community, I understand that the main criticism of the community is that there is a single experiment, right? This is probably the main, which I can understand. Actually, since I discuss a lot with LSCB, I see that for B2S mu, they really done these B2SLL observer, they've really done a very good job. So I don't think there is any problem there. It's hard to believe, but okay, of course, another experiment would be helpful. For the charged current anomaly, which is very important for all this picture, the situation is much more uncertain, I have to admit. I mean, the 3 sigma, we have seen 3 sigma going away easily. So there I'm more cautious. And I admit this is the big pillar of all our construction, because it's the biggest effect in terms of absolute size. Concerning the true IPT, like this tau tail, there is really a bit a question of luck, because it change a lot depending on the precise, if the anomaly is a factor of 2 bigger or smaller, which is everything is compatible in terms of IPT, can mean 5 years or 20 years. Okay, so it's one has to be a bit lucky. Therefore, I don't know. I cannot really make a commitment. I think there is a hope, but indeed, I understand that they tend to be optimistic, so I don't want to make a claim on the date. But on the other hand, I believe there is something there. I mean, on BSLL now, really, I don't see how this could be scrapped, because it's the consistency of the different result which is striking.
And you said that some of them are not related to the electron reconstruction, and not all of the.
Yeah, I mean,
yeah.
the SB mu alone, for instance, has nothing to do with the electron reconstruction.
No, exactly. Yeah.
All
You mentioned some.
these angular observable has nothing to do with the electron reconstruction, but also those which have to do with the electron reconstruction. The efficiency, I mean, they measure it really. They've done a beautiful analysis on this RK, looking, of course, as a control channel using the JEP-psi. You see, the JEP-psi is at a different energy, but this is not relevant for the experiment because at the end, everything is boosted. So what matters is the momentum of the electrons. And so they really separated the different kinematic region in such a way that they can mimic the signal. So on the efficiency, I think they have a good control. Maybe the most difficult thing is probably the background more than the efficiency, because the rare mode is rare. Therefore, they really have to describe any single channel. So if I don't think there is a problem, but if there is a problem, in my opinion, it could be more in the background in this really complicated hadronic environment. Also from other BDKs, where you miss something. This is why I think Bell would be fantastic. I mean, that's what really we should really hope that they will get it soon.
And there, the time scale is more order 2 years, 5 years.
I think well, first they will first see the charged current anomalies, which is a bigger effect. And I think for the charged anomaly could be some 2 to 3 years for the charged current. And of course, if they see the charged current, I'm sure everybody will start to believe also the neutral current. For the neutral current, it's a question of statistics, is probably more. So more than, I think more than 5 years. But the good thing is that I think year by year, we will have some progress. So I hope to see a smooth shift of the community. In a sense, from this point of view, it's a bit different than G-2, where I think that G-2 is there isolated. I don't see how much we can, it's difficult to, well, maybe the lattice result, of course, can do some progress, but it's more complicated.
That you don't have an explanation of that, if it's true?
Well, that actually, if you want, I have some slide.
In this context, yeah.
In this context, I think it's difficult to feed the G-2. You see, it's not obvious how to reconcile G-2. First of all, it's always necessary a loop effect, so it's not tree-level. So it's more difficult to identify what happens there. Can be some light things or some heavier things, even super light. What bothers me, actually, we did a paper on that, is that you need the strong Flavor alignment to protect mu2 gamma. This is the things that really bothers me more about G-2. So in this multi-scale picture, really it's difficult to protect mu2 gamma. So this is why I have difficulty to put it into the game. One can do it, people have done it with, but really start to become very baroque because how to protect mu2 gamma. That's why for the moment, I'm a bit agnostic. I mean, if G-2 is there, I think it requires extra ingredient. Let's put it that way. Like a big violation of chirality, maybe only in the lepton sector. So what I missed there is really the link to the Yukawa coupling, which on the other hand seems to be very nice fitting in this other picture. But we have to wait.
This actually brings me to another small question I had. So the coupling to lighter generations is way more suppressed, but given that we have more precision in some of these observables, could some channel be comparable or competitive with these searches? I don't know, can mixing, could it be, even if
these
the coupling
things are, no, you're right, it's a good question, but I think are within the present error. I mean, for instance, KK mixing or Beaver mixing, where we have first family, given the present precision, which is some 10% of the experimental, 10% of sun model contribution, that is the size aspect here, given the extra loop suppression. So it's not inconsistent that we have not seen it. One thing again, that would be a super striking signature, but it's difficult, is tau to 3 mu. I mean, tau to 3 mu you expect in this case, and there I was hoping, for instance, CMS also could do it, but apparently it's not easy, because 3 muons accidentally come from also that you have misreconstructed muons. So going below 10 to minus 8, so in the ballpark here is will be more 10 to minus 10, it's difficult.
And improving on KK bar mixing or mu2 gamma you were mentioning now for the
mu2 gamma, mu2 3, I mean, these are all interesting. It's again, but also on the first generation, we have more uncertainty on which is the exact
the expectation.
Yeah. So I think it's very important to could be around the corner, but if it is one order of magnitude more, we cannot exclude it at all. Actually, nice. It's somehow in between 2 order of magnitude between present data and the future. Since so 2 order of magnitude is a big range.
Yeah.
But it's in a sense is much, for instance, mu2 3 becomes in a sense more interesting than mu2 gamma, which actually this is interesting because this is 3 level while mu2 gamma it's 1 loop. Also mu2 conversion is interesting in this setup. Again, everything has been checked and with a reasonable mixing angle, we are consistent with present data, but in the ballpark of future generation. I would say, I mean, trying to be honest, I mean, there are the things we have to tune because it's, I mean, it's a bit the alignment of these new physics with respect to the down direction rather than up, which is not striking, but is a kind of 10% alignment to deal with the B sub D mixing. Otherwise, you could have expected something bigger in B sub D mixing, but you don't see. This, I would say, is the ugliest thing. And also, I mean, the fact that the coupling, okay, it's relatively big. I mean, factor of 2, 3 for the gauge coupling. I mean, more 3 than 2, especially given this bound from coloron. Again, I don't know if you will consider it bad or not, but.
Before we close the recording, maybe and continue to chat a moment together, is there a last urgent question? No, then we can start to think more freely about what will be the future of flavor physics. Let me stop the recording.
Okay.
And maybe we can thank again Gino and we continue chatting a moment together for a while.
Thanks. Thanks for the pleasure.